There's two parts to today's lesson. The first part we'll be learning about something called the reaction quotient, which is symbolized by the letter Q or QEQ. And then after that, we'll be learning about another K value called KSP. So the first topic is going to be that reaction quotient. So far, all of the equilibrium problems that you've seen have only started off with reactants. So when you look at Le Chatelier's principle, you know the reactants are going to be converted into some products and equilibrium is going to be established. So we always saw a shift from reactants to products. What the reaction quotient does is help us figure out which direction the equilibrium is going to proceed if you start off with a little bit of everything. So let's say you put some of your reactants and products all together in a system and an equilibrium sets up. Which way is it going to shift? Is it going to go forwards? Is it going to go reversed? Is it going to shift at all? Those are some things we'll look at with the reaction quotient. So as I just mentioned, the reaction quotient, we use the letter Q, or sometimes a Q with an EQ, to represent this value. And like we just said, it is used to predict the direction in which the equilibrium must proceed in order to actually reach equilibrium. It's very easy to calculate. When you're doing a calculation for Q, you do the same expression that you would for KEQ. So you write your products on the top, reactants on the bottom. Exponents work the same way with the coefficients. But when we used KEQ, everything was at equilibrium. For QEQ, you're going to use your initial concentration of reactants and products. So that's something different. Not at equilibrium, it has to be initially. So once you actually get a Q value, what you're going to do is compare it to KEQ. And then there are three different possibilities which will tell you which way the reaction is going to proceed. So if you calculate a Q value and the K value is still larger, what that means is the reaction is going to still proceed in the forward direction. It's going to make more products. If you do a calculation and your Q value happens to be the same as the K value, what that means is the concentrations are actually perfect for equilibrium conditions and you won't notice a shift. The likelihood of that happening is pretty low, but it's still a possibility. The last option, once you calculate Q, if it ends up being larger than K, that means it's going to favor the reverse reaction, or it's going to make more reactants or go in the reverse direction. So what we'll do next is try out a problem so you can see how it works, and hopefully you'll see there isn't a lot to calculating Q. So let's take a look at the problem together. You have 3 moles of hydrogen iodide, 2 moles of hydrogen, and 1.5 moles of iodine. They're placed in a 1-liter container. Again, if you see the temperature like it's listed here, that just means that it's constant. And we want to know which reaction takes place. So which direction is what it's asking for here. So if it doesn't say which direction specifically, it might say just which reaction, but it means which direction. You should also be given a K value for the reaction. So for this reaction at 448 degrees Celsius, the K value is 50. Okay, so now what we're going to do is write a Q expression that looks like K, but instead of putting KEQ, we're going to put QEQ. On the other side of the equal sign, it's going to look identical to your K, so your product's on top, so the hydrogen iodide. And then on the bottom, you've got hydrogen and iodine. So other than the Q part, this should look the same as a K expression. But now we're going to go in and put in our initial values. So initially we have 3 moles of hydrogen iodide. It's in 1 liter. So it's just 3 moles per liter. Make sure that you square it. And then when we put in our products from our question, let's just put that back up. You've got 2 moles of hydrogen in 1 liter, so 2 moles per liter, and 1.5 moles of iodine in 1 liter, so 1.5. So on the bottom, we're going to put in those numbers. This is a nice, easy number to work with, and you should end up with a QEQ of 3. So now what we have to do is compare our QEQ to our KEQ. So let's just put this over here for reference. QEQ is equal to 3. The question told us that KEQ was 50. So which one is larger? KEQ is larger than QEQ. And from our options up here, if we go back up, we've got a scenario like the first one here. K is larger than Q, so it's going to proceed in the forward direction. Now, there are some questions that would just apply a question like this, so just to predict which direction it's going to move in, but some of the higher level types of equilibrium problems would get you first to do a QEQ calculation, figure out which direction is shifted in, and then based on that, you set up an ice table and solve for equilibrium concentrations. Those are generally ones we don't see in high school at our level, but you could apply it in future problems if you do take more chemistry. So that's our quick overview on QEQ. So now what we're going to do is move on to another topic, same lesson. And these ones are dealing with slightly soluble ionic compounds. So you might remember a little bit about solubility from grade 11. Used a solubility table to figure out whether something was aqueous, meaning it's soluble, or something was going to form a precipitate, meaning insoluble. And then there were a class of compounds you might have remembered that said slightly soluble or very little bit will dissolve, something like that. So those ones work a little bit differently, and those are going to be the focus for what we learn about in grade 12. So that's where equilibrium comes in, and that's why we see that here. So when a solid is placed in water, we know ionization can occur. So that means some of the ions are going to break apart from the compound. For many salts, though, many ionic compounds, only a little bit can actually ionize. And for those ones, an equilibrium system is established. And what happens there is the rate of ionization, that's the rate where you actually form your ions, equals the rate of the ions joining to reform the salt. So that's the reverse direction. So in the forward direction with this example here, barium sulfate solid dissolves in water to make some barium and sulfate ions. But at the same time, if some of those ions recombine, you get the reaction going in reverse, and it reforms that solid there. If you take a look at the states, you'll notice with these types of problems, we have different states. There's a solid for our ionic compound, and then there's 2 ions in aqueous solution. So these ones here are examples of heterogeneous equilibrium problems. And if you remember way back from the beginning of the unit, with heterogeneous equilibrium problems, we don't include solids or liquids in any K expression. So you'll see that in a minute. That's also true here. So what we're going to do next is look at how to actually write out a K expression for a salt. So we're going to use the same example with barium sulfate. This K is a little bit different. Capital K is always for equilibrium in this unit, but the little subscripts tell you a little bit more about what type of equilibrium is established. So for this one, it's called the solubility product constant. So the constant is the K, and solubility product is the S and the P. So to write out a KSP, we're not going to include the solid. Okay, so we're not going to include that at all. If we're not going to include that at all, the only thing that we're going to include in KSP are going to be whatever ions form. So same as before with other K values, write your KSP. Any coefficients in front still become exponents. Here they're both 1, so we don't have to worry about that. So we've got barium ions in brackets, and we've got sulfate ions in brackets. So here we've got a KSP expression for that salt. If you're looking at it, it does look a little bit easier. There's nothing in the denominator, so solving for equilibrium concentrations is a little bit easier. In your textbook, in the appendix, and I would suggest taking a look at this either now if you want to pause the video or after, there's a table of KSP values. Sometime you need to look up those values. So if you need it for a question, just take a look back there. You'll see there's quite a range in KSP values. Some are 10 to the negative 5. Some can go over 10 to the negative 20 or negative 30. So it's got quite a range of solubility on there. In general, though, you can look at the value of KSP to give you an idea about the solubility of a substance. So smaller KSP values, like the really tiny ones, then I'll just make a note up here, they can be up to around 10 to the negative 30 factor. Those ones are ones that indicate the salt is very, very, very low in solubility. The ones that are larger when we deal with KSP, large is still not very big, but they could be 10 to the negative 3, 10 to the negative 5. Those are ones that are maybe a little bit bigger. In comparison, their solubility is a lot higher. And when we deal with solubility, we know that directly relates to concentration of ions. So if something's more soluble, you're going to have more ions in solution. If something's less soluble, you're going to have a lower concentration of ions in the solution. So you can even look at the KSP and decide, am I going to get a lot of ions or not when the salt actually dissolves in water. So make sure you take a look at that table just so you can see the range and different types of salts that are involved. So now what we're going to do is practice some problems involving KSP. So if you don't have your calculator out by now, make sure you've got it handy because I'm going to give you some time to practice the problems as we work through them together. So the first thing that I want you to try on your own is to write a solubility expression for calcium phosphate. So just like what we did for barium sulfate on the previous page, but do it for calcium phosphate. And a hint, the first thing you want to do is write out an equation that shows how calcium phosphate dissolves in water. So take a minute, pause the video, and see if you can write out a KSP and an equation for dissolving. All right, so hopefully you gave that a shot. Let's take a look first at the equation for calcium phosphate. So calcium phosphate, if we're assuming it's starting off as a solid, we would write it with its formula just as a solid like that. Put in our equilibrium arrows. And then our two ions are the calcium ion and the phosphate ion. If you need to go back and grab your periodic table and your list of polyatomic ions to make sure you've got the charges and everything correct, definitely use whatever you need to. Those are tools that you can always have when needed. So calcium, there are 3 of them. So make sure you don't forget to put a 3 there in front of your calcium ion. It's got a charge of +2 and it will be aqueous. And then phosphate, there are two of them. And phosphate, remember, has a charge of -3. And we're going to put aqueous in there. Writing out an equation first for your solubility questions is really helpful just to make sure you have the right number of ions and the charges that are there. Once you've done that, then you can write your KSP. So again, remember, solids aren't included in your KSP. You can completely ignore them. So we just need to include our two ions. So my first ion is the calcium ion, but here I've got a coefficient of 3, so I need to put an exponent of 3. Next to it goes phosphate, so PO4, 3 negative, and then make sure you put a 2 in for the coefficient that's there. So if you're just asked to write a basic solubility product expression for a salt, that's all that you need to do. Write out your equation for dissolving, then write your KSP. Do not include the solid for the salt. Okay, now let's try out a couple of problems involving ice tables. Yes, ice tables come back again in several different ways in this unit. Here's one with solubility. They're worded differently, but the problem-solving process is very similar. So once you figure out what they're asking for, when you start to solve these problems, you realize that, yeah, they are pretty similar to ones that you've seen before this. So let's read through. The solubility of barium fluoride is 7.52 times 10 to the -3 moles per liter at 25 degrees Celsius. Calculate the KSP of barium fluoride. So let's look first at what we've got. Anytime a question refers to solubility of a salt, they're referring to something at equilibrium. If we're looking at solubility, we're going to assume an equilibrium has been established. So any mention of the word solubility with these problems is referring to something at equilibrium. Next, we actually have a value, 7.52 times 10 to the -3 moles per liter. If they give a value to you, that means this is a concentration at equilibrium. You took your salt, your barium fluoride, you put it in water, you mixed it up, and the solubility was measured at equilibrium. So this is important to keep in mind. Now what we're going to do is go and set up our ice table. So first thing you need is your salt, barium fluoride, and it always starts off as a solid. This question gave us the formula, so we can use it right away. Put in your equilibrium arrows, and then your ions. So barium has +2. There's one of them, and there are 2 fluoride ions. There we go. And just like before, we're going to write ICE. Since we're not doing anything with the solid, I just like to cross it out. Your textbook sometimes puts in information for initial and change, but there's nothing at equilibrium. I just prefer to cross it out, so that's what I would suggest that you do. Cross out the solid, nothing's going in there, you're never going to need to use it. Next, when we go and fill in information for our 2 ions, we're going to fill it the same way as we did with other problems. So initially, we're going to assume there's no barium or fluoride ion present. Absolutely none. So if it's dissolved in water, there's none or 0. So I'm just going to cross it out. Then we fill in our change. We know some of these ions are going to be produced, so we're going to have an increase value. Here we're going to have 1x for 1 barium, so this will just be x. And over here with the fluorine, plus 2x because there are 2 fluorines, and then 2x. So there's our ice table. And now what we want to do is solve for KSP. So if we're going to solve for KSP, that means we need our barium ion concentration and our fluoride ion concentration. So we need a KSP expression. Since they give us, back up here in the question, that molar concentration, that's already at equilibrium. So what that actually means is this is our X value. They've given that to us. So what we can do now is actually put that into our table. 7.52 times 10 to the negative 3 is x. And then over here for the fluorine, because there's two of them, we need to double that. So I always like to fill in my ice table first, just so I don't miss these things like the multiplying. And then I can go and do my K value after that. Okay, so now we've got our concentrations at equilibrium in the right proportions, and now we can go ahead and solve for KSP. So if you want to try it, you can pause the video and plug in the values and see what you get for your KSP. So now if we do a check together, we're going to put in all of our numbers. And when we calculate, you should get something that looks like this. 1.701 times 10 to the negative 6. And then for this question, we need 3 significant digits, so just make sure that you round at the very end. And there you go, there's your KSP for barium fluoride for this question. Let's try out one more problem that's very common with KSP. So one problem, like we just saw, has you calculate a KSP value. The other type of question might actually get you to calculate a solubility. So this problem is very similar to the first one, but we're solving for something a little bit different. So let's get it set up, and then I'm going to let you try it out, and we'll take everything up together. So we've got silver chloride. It has a KSP value of 1.6 times 10 to the negative 10, very small. What is the molar solubility of silver chloride in water? If they're asking again for molar solubility, what this means is find the concentration at equilibrium. What is your concentration at equilibrium? So even though it doesn't say that in the question, that's really all that we're doing. So based on that, if you think you can try and solve it, why don't you go ahead first and set up an ice table, and after that, see if you can use a KSP expression and the actual KSP value given to solve for that molar concentration. And when you're ready, unpause the video and I'll go through the answer with you. All right, so if you've given it a shot, let's take a look. First thing you need always, write out an expression. So silver chloride solid, silver ions, and chloride ions. And then we're going to write in our ice table here. Always cross out the solid, makes it a lot easier. Since it's starting off in water, we're going to assume pure water has no silver or chloride ions. And we're going to increase the concentration of both ions. Both are 1x because there's one silver and one chloride ion. So at equilibrium, we just have x and x. This is different from the previous problem because we don't have any information about x. That's what we're trying to solve. But we do have a k value given in the question. So now that you've got that ice table down, now we need to use our KSP expression to solve. So silver and chloride ions. We're going to fill in our KSP here. That's 1.6 times 10 to the negative 10 given to us in the question. And both of these are just x. Now looking at that, hopefully you can see it's fairly straightforward to solve. A lot easier than some of the other K problems because you only have the two ions. So you end up with something that looks like x squared. So if you take the square root of both sides, you should get x is about 1.26 times 10 to the negative 5. And then when we round it, two significant digits should be 1.3 times 10 to the negative 5. And remember, because this is solubility, make sure you put in moles per liter. So that's our lesson on QEQ, our reaction quotient, and KSP, solubility product constant.